Hi, welcome back to Moose in Chemistry. VSEPR theory, model, octet rule, and exception lessons. Just when you think it couldn't get any more stranger. And for our inspiration, we have a little bit of Mozart for a moment here. This is supposed to make us a lot smarter. All right, thank you, Mozart. All right, now, so there are a lot of exceptions in chemistry. Chemistry is not either black or white, but it's a lot of gray. Because every time when we teach chemistry, this is the way it's going to be, but then there's always that exception. And we love exceptions. So why do we have exceptions? Well, first of all, when we're doing the octet rule simply states that you have to have 8 valence electrons in the outer shell, right? That's what it's all about. Well, there are some atoms out there that can be stable without 8 valence electrons. Case in point, guys, hydrogen is perfectly stable with 1 valence electron. Helium is perfectly stable with 2 valence electrons. Okay? So now, let me see what else we've got going on here. Look at boron. Boron is in group 13, and it's perfectly stable with 3 valence electrons. And, of course, beryllium is stable with 2 valence electrons. So here's the general rule. When do you have to have the octet? So let me write that down. When do you have to have an octet? Okay, which elements basically? Well, think about this. Periods in period 2. You say, well, hey, isn't boron in period 2? Yes. But the elements that have to have the octet, for sure, are carbon in period 2, nitrogen, oxygen, fluorine, and neon. All those have to have an octet. Now, why is that? Because these guys are based upon 2s2 and 2p6. Look at that. 2 plus 6 is equal to 8. So there are no D shells. In period 2. So we can't expand the octet, right? So we're kind of like, that's it. So when can you violate the octet rule? You violate the octet rule in period 3 and up. Because period 3 has 3s2, 3p6, and then, of course, 3d10. There are D shells in period 3. So since they're D shells, we can expand the octet. All right, so let's think about this for a second. So let's look at another reason for the exceptions, okay? Again, expanded octets are because of the D shells, and the reason why period 2 can have an expanded octet, because there are no D shells. Okay, let's see what else we have under exceptions. There's also something called a dimer. Now, a dimer, guys, is really, really weird. For example, let's look at NO2. So we're going to talk about a dimer. Now, a dimer is a structure that has a unpaired electron. Notice I didn't say unpaired share. It said unpaired electron. So when we do nitrogen, right? Let's do it here. Let's try NO2, for example. Okay, so NO2. So we go, nitrogen's in group 15, remember? So it has 5 valence electrons. Oxygen is in group 16, so it has 6 valence electrons. Having fun? Yeah. So nitrogen is 1 times 5 electrons, and oxygen is 2 times 6 electrons. So this gives me 12 electrons and 5 electrons, which gives me 17 electrons. Notice that there's no charge here. There's no negative. There's no positive. Doesn't exist. All right. So now what are we going to do? We're going to create something called a free radical, which is also another name for a dimer. Free radical equals dimer. Okay, just want to put it out there. So when we do our structure, we're going to go N and O and O. Now, let's go ahead and connect our O's, right, to our N's, and then we're going to fill in our electrons here. So we got 2, 4, 6, 8, 10, 12, 14, 16, whoa, wait a minute, 17. So there's that one dot by itself. So nitrogen has only got 4 electrons in there. Remember we said nitrogen had to have an octet. Well, there is an exception here. So what we're going to do is we're going to take this nitrogen and we're going to put these 2 electrons right here. So we're going to double bond this. Single bond here. Right? So, and then we're going to have 1 dot right there. So let's see what we got here. 2, 4, 6, 8, 10, 12, 14, 16, 17. There's 17 dots there. All right? But you know what? That means that this is going to have a plus charge. So we have to put a plus charge there. And it's actually kind of this 1 dot right here bends things. So it's going to actually look more like this. Now, in a radical situation, we would put a bracket around this, right? But we're not going to do that because it's a free radical, and we're not going to use the brackets. Also, who's to say that it's this oxygen that's getting the double bond, right? So this could also look like this. Okay, so it can look like that. So that's another type of an example of a structure that it's an exception to the octet rule, because you know that nitrogen should have an octet, but in this case it doesn't. All right, so now let's clear these drawings here, and let's look at one more thing. So I'm going to go ahead and clear all these drawings. Okay. And now the last thing I want to talk to you about, let's see here. Oh, yes. Like, for example, let's look at beryllium hydride. Now, okay, all right, I know. Hey, this is an ionic compound. So why would we be doing a VSEPR model for it with sticks and dots? The answer is this. This is an exception. Beryllium is a big exception to this whole bit of ionic compounds and covalent compounds. So the theory is, so nothing is completely covalent or ionic. BeF2, let's change this to BeF2, I'm sorry, let me erase this H there and make this an F instead, because that would make more sense. Now, okay, Be is extremely ionic and F is extremely polar covalent. So F has a high electronegativity, which means it has the ability to draw electrons to it. Be is highly polarized itself and really doesn't want to give up an electron. So what's going to happen when we get this situation is, yeah, I know, don't shoot the messenger, but here it goes. So Be is in group 2, of course, and it has 2 valence electrons. And let me space this out a little bit here. And I know I'm going to get slapped by you in class, and you're going to go, oh, why did you do this to us? But it's a reality, guys. So fluorine's in group 17, and it's only with beryllium. So we're going to go ahead and put the dot there. And now that's 7 valence electrons. So when we do this, we got 1 times 2 valence electrons, and F is going to be 2 times 7 valence electrons. So this gives me 14 valence electrons. This gives me 2 valence electrons, which gives me a total of 16 valence electrons. So now maybe I should probably put some Mozart in here, because I think it's going to drive us all crazy. But, you know, we need to kind of push on with this. So this structure is going to look like this. And here it comes, guys. I know, I know, I know. Ooh, look at this. I connected these electrons as if they were being shared. And that's a big no-no for ionic. But in this special case, it does work. So these electrons are actually being shared. And so this is the correct structure for barium fluoride. Okay? Barium fluoride is technically a covalent structure. I know it looks ionic, but in this case, it's not. And these are extremely rare, but I wanted to give to you this other exception. Okay, guys. So now, I hope you have an awesome time today, and you have an amazing day, and we'll see you back at mooseandchemistry.com. And if this is really confusing, let Mozart soothe the way. Did it help? Nah, maybe not. Okay. Anyway, be snarly, be awesome.